Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can drift a little more slowly, and where complicated ideas loosen into soft shapes you can hold without effort. Tonight's journey will take us into something bold, almost mischievous, the dream of building a time machine, not the flashing lights or spinning rings of science fiction, but the deeper, quieter question underneath them. What would it mean to truly design such a thing, not just in imagination, but as an engineering challenge written directly onto the fabric of space-time? And what hidden obstacles would rise from the moment we take that idea seriously? Before we wander too far, you're welcome to take a slow breath. Maybe dim the lights a little, or let the room settle into whatever sound feels gentle to you. If you'd like, imagine yourself floating somewhere between familiar starlight and the soft dark of deep space. The air around you is calm, nothing rushes, time feels less like a straight line and more like a quiet lake surface, smooth, patient, waiting. This is where our story begins. Tonight, we'll drift together through the architecture of space-time, the strange fuels that might hold open a tunnel through time, the shields and safeguards needed to keep reality from unraveling, and the quiet truth that time travel is as much a human question as it is a scientific one. But we'll take it slowly, allowing each idea to settle like dust in a sunbeam. There will be no hard symbols, no abrupt equations. If we mention something like energy equals mass times the square of the speed of light, we'll cradle it gently, letting it pass by like a soft wave instead of a technical barrier. So if your mind begins to wander, let it. If your eyes soften or grow heavy, that's perfectly fine. You're not here to memorize, you're here to drift. And somewhere in that drifting, the idea of designing a time machine may become less of a puzzle and more of a quiet conversation with the universe itself. When you're ready, we'll take our first small step into the heart of the idea, not by asking how to build a time machine, but by asking what we're really trying to shape when we imagine bending time at all. If you close your eyes and picture a time machine, the image that arrives is probably vivid. Maybe it's a shining metal capsule, humming with electric promise. Maybe it's a chair surrounded by swirling rings of light. Or maybe it's something as simple as a dashboard with glowing digits, waiting for you to type in a year. These images are familiar because stories have been drawing them for decades. They give us something solid to imagine, something that looks like a machine we might actually plug into a socket or start with a key. Reality, however, begins somewhere quieter and perhaps stranger. If a real time machine were ever built, its first component wouldn't be steel or glass. It would be space-time itself, the invisible fabric that carries every moment we live. And instead of bolts or engines, the first tools we'd need are understanding and imagination. Not the frantic kind of imagination that sparks fireworks, but the slow, steady kind that watches a river flow and wonders how far beneath the surface the current truly goes. To design a time machine, we must first gently set aside the idea that time is a straight line ticking away on a clock. In everyday life, that's exactly how it feels, seconds falling forward in a steady rhythm. But physics paints a softer, more flexible picture. Time stretches. It bends, it slows down when you move very fast, and it lingers when you're deep in a strong gravitational field. A clock on a satellite ages just a little faster than a clock on Earth. A clock carried on a plane ticks differently from one left on the ground. Even climbing a mountain changes the tempo of your personal time just a little. These effects are tiny in daily life, but they whisper a remarkable truth. Time has texture. And if something has texture, it can be shaped. Imagine the universe as a vast sheet, not a rigid one, but something like a soft fabric floating in darkness. Mass and energy create gentle dents in this fabric, and objects move along curves formed by those dents. Light bends when it passes near the sun not because it chooses to, but because the sun bends the fabric underneath it. You and everything you know follow these curves every moment, curves not only in space but in time as well. If you could push or pull on this fabric, if you could fold it or twist it just slightly differently from how gravity already does, you could guide the paths that objects take through time. This is the essential idea behind time travel in physics. Not a machine that moves through time, but a machine that reshapes the geometry of time itself. But geometry here is not about triangles or circles. It's about the rules that decide how far apart two moments are, or how long a second lasts in one place compared to another. When Einstein wrote his famous relation between energy and mass, that energy equals mass times the speed of light squared, he was describing how matter and energy can influence this geometry. If enough energy is gathered in one place, space bends, time bends, the path through them shift. Science fiction likes to imagine time machines as devices with dials and glowing switches. In reality, the dial you would turn is space-time itself, and instead of glowing blue arcs, the machine's true engine would be mass, energy, and the way they sculpt the universe's structure. The question becomes quieter, more intimate. If time is a landscape, what kinds of hills, valleys, or gentle loops would allow someone to walk forward and arrive at a moment that lies behind them? Physics does not laugh at this idea. It answers with possibilities, a tunnel between two distant points called a wormhole, a massive, spinning tower that twists time into a spiral, or a small bubble where space compresses in front and expands behind, carrying a traveller like a boat on a wave. But each possibility comes with hidden challenges. How much energy does it take to carve a tunnel in the fabric of space-time? How do you keep such a tunnel open against the universe's instinct to flatten it? How do you guide a bubble of distorted time with the precision needed to arrive at the right moment, not 1,000 years early or 1,000,000 years late? These are questions we'll explore slowly, gently, without rushing toward any final answer. Because designing a time machine isn't about finding a blueprint. It's about understanding the quiet rules that time already follows. And once we understand those rules, we can imagine, with a little more grounding, what it might mean to invite them to bend in unusual ways. For now, it's enough to hold this first image. Not a machine with wires and panels, but a calm, invisible stage on which every moment unfolds. If one day we learn to reshape that stage, even slightly, the flow of time itself might begin to feel less certain and more full of possibility. When we talk about time in everyday life, it feels like the most familiar companion we have. It sits quietly on our wrists. It glows from our phones. It measures out our days with the calm regularity of a heartbeat. You wake up. You move through your morning. You watch afternoon light dissolve into evening, and you rarely stop to wonder whether time itself might be doing something far more flexible, far more subtle than simply ticking forward. Yet hidden beneath the calm surface of routine, time is constantly shifting. Stretching here, slowing there, lifting or sinking depending on where you stand in the universe. And to understand what it means to bend time, we need to gently lift that surface and look just a little deeper. A quiet way to begin is with something familiar, a clock in motion. Many experiments over the last century have shown that when a clock moves very fast enough to feel almost like a whisper against the speed of a light, it ticks more slowly than one left at rest. If you imagine two identical clocks, one kept on the ground and one flown around the world in an airplane, you might think they'd reunite perfectly in sync, but they do not. The one in the airplane ages just a little less, by an amount so tiny that only extraordinary instruments can detect it, yet it is undeniably there. It is as though the moving clock took a shorter sip from the river of time. A similar effect happens with gravity. If you bring a clock up a mountain, even just a few thousand meters above sea level, that clock ticks slightly faster than an identical clock left in a valley. It's not something you'd notice in your daily life. No one ages dramatically while hiking. But the difference exists, and satellites orbiting above Earth must constantly account for it, or else our navigation systems would slowly drift into confusion. These quiet differences whisper something profound. Time is not a rigid universal rhythm. It is shaped by motion and by gravity. And gravity itself is nothing more than the way mass and energy shape the space and time around them. This idea, introduced by Einstein, is often explained with the metaphor of a soft fabric. Imagine a large sheet stretched out smoothly. If you place a heavy ball in the centre, it sinks into the sheet, and smaller objects nearby slide gently toward it. This is a picture of gravity not as a force pulling, but as a curve in the landscape. Now stretch that idea further. Not only space, but time is curved by mass and energy. The presence of something massive doesn't just bend the space you move through, it bends the tempo of your moments. Near something heavy, time itself slows. You can think of this slowing as a kind of stretching. If two people stand in regions with different gravitational strengths, one close to the surface of a dense planet, the other far away in calm space, their seconds won't match. One person's minute will be ever so slightly longer or shorter than the other's. And though the difference is tiny in our daily experience, the universe takes it seriously. Light takes different amounts of time to move past a planet than it would if that planet weren't there. Clocks drift, orbits shift. Everything responds to the quiet warping of time. This flexibility is what physicists mean when they speak about bending time. They are not imagining time as a substance you can grab and twist like taffy, but as something whose pace and direction can be influenced by mass, energy, and motion. If you could gather enough energy in a small region, energy measured not in watts like a light bulb but in quantities so large they defy common comparison, you could, in theory, bend the flow of time dramatically. To picture this without drifting into equations, imagine walking along a gentle slope in a landscape. Most of the time, the slope is so slight you don't notice it. The ground feels level, but occasionally you reach a steep rise or a deep dip and your pace changes. Time behaves similarly. Most of the universe is a quiet meadow of near flatness where time flows uniformly. But near a black hole, for example, the landscape becomes steep, so steep that time slows to a crawl for an observer close to its edge. If someone were to drift near such a place, they might experience a few minutes while years pass far away. That difference in tempo is a tiny glimpse of what bending time truly means. And if we can imagine building structures or machines that create similar distortions, gentle dips, steep wells, or even loops, then we begin to imagine how a time machine could exist in principle. Not as a device that overrides the laws of nature, but as one that works with them, arranging mass and energy in such a precise way that the flow of time takes a new, unusual path. One of the most remarkable ideas born from this perspective is the possibility of shaping a path that curves backward in time. It's as though a hiker walked forward on a mountain trail only to discover that the path winds around and brings them back to the place they started. Except here, the place is a moment in the past. Physicists have formal names for such loops, but we don't need those names yet. It's enough to imagine a road through the landscape of time that arcs gently behind you while you continue to walk ahead. But shaping such a loop is not like mapping out a trail in dirt. It means influencing the tempo of time across vast distances, arranging gravitational dips and rises with extraordinary precision, It means understanding how light, matter and energy will respond, how the fabric will twist or soften. And before you can design any kind of engine to travel through time, you must learn how to design the landscape itself. This is where the idea of a time machine begins, not with gears or switches, but with a new way of seeing time as something dynamic, something whose flow can be gently persuaded by mass and energy. The dream of time travel becomes less like magic and more like a quiet kind of architecture woven into the universe. If the fabric can be shaped, then the question becomes, how far can that shaping go, and what structures could hold the shape open long enough for someone to pass through? That will be our next gentle step as we begin sketching the earliest architectures of a machine that touches the river of time itself. When people first hear that time is flexible, that it can stretch and tilt and slow depending on the energy around it, the imagination immediately begins to wander. If time can be shaped, then perhaps it can be sculpted. If it can be sculpted, perhaps it can be curved. And if it can be curved, perhaps we could make a gentle loop in it, like bending a strand of glowing ribbon until two distant points touch. Physicists have spent decades exploring this idea by drawing what you might call sketches on the fabric of space-time, early, tentative blueprints for machines that might change how time flows. These sketches aren't blueprints in the engineering sense, but they are maps of possibility, born from equations but describable in images and stories. One of the most enduring sketches is the wormhole. If space-time is a kind of cosmic sheet, a wormhole is like folding that sheet so two distant regions touch, then making a tunnel between them. It's not a hole in space in the usual sense, but a shortcut through the landscape, like stepping off a winding mountain trail into a tunnel that comes out miles away. Most versions of this idea look like two openings, often compared to mouths, connected by a throat. If you travel through the throat, you emerge not only in a different place, but potentially in a different time. What makes wormholes interesting for time travel is not simply that they connect two distant points, but that the two ends can experience time differently. Imagine holding two clocks. If you keep one still and carry the other on a journey, moving it near heavy objects or accelerating it close to the speed of light, the two clocks will no longer agree. This is the natural stretching and slowing of time we explored earlier. If each mouth of a wormhole is like one of those clocks, then by moving one mouth around in a clever way, you can create a time offset between the two openings. That offset becomes a tiny temporal doorway. Enter one side, and you might exit on the other side at a different moment, perhaps the past. In stories, this often becomes a dramatic device. In physics, it is a quiet but astonishing possibility. Yet wormholes are not gentle tunnels by nature. Their throats tend to collapse instantly under gravity, pinching shut before anything can pass through. To hold one open, you'd need something that behaves in a way ordinary matter doesn't. Something that pushes outward instead of pulling inward. Physicists call this exotic material negative energy, not because it glows with danger, but because its density dips below the usual level of empty space. The idea sounds abstract, but it traces back to subtle laboratory phenomena where the vacuum itself behaves in unusual ways. Still, the amount required for a full-size tunnel would be enormous, far beyond anything we know how to produce. Even so, wormholes remain one of the most evocative sketches, a tunnel in the universe, held open by strange energy, its two ends drifting through time at slightly different rhythms. Whether such a thing could ever be built is uncertain, but the sketch itself is a doorway into deeper curiosity. Another sketch comes from imagining a tower spinning in space, so massive and so fast that it pulls space-time into a slow spiral around itself. This idea grows from the fact that rotating objects can drag the fabric of space-time along with them. Earth does this gently. A rapidly spinning neutron star does it dramatically, and in theory, if you had a cylinder so dense and spinning so swiftly that it skirted the edges of what matter can endure, it could twist time into a loop around it. Walking around such a tower might bring you back not just to the same place, but to an earlier moment. Of course, there are challenges. A tower long enough to create the right kind of loop might need to be infinitely long, a concept as impractical as it sounds. And even if it were possible to build a finite version, it would require densities and speeds that stretch imagination to its limits. But as a sketch, it teaches something valuable. That motion, especially extreme motion, shapes time in surprising ways. You don't need to tear open space. Sometimes you just need to twist it. Then there is the idea of a warp bubble, which became widely known through imaginative theories, suggesting a way to move faster than light without breaking the rule that nothing can outrun light locally. The thought experiment is gentle enough to picture: a bubble of calm space surrounding a ship, while the space ahead of the bubble compresses and the space behind it expands. If space itself moves, the ship inside can ride the wave like a boat carried by a swift current. Nothing inside the bubble actually moves faster than light. Instead, the bubble drifts through the universe on a shifting patch of space-time. To adapt this for time travel, you might imagine shaping the bubble so that the path it takes bends backward into an earlier moment. This is where the idea becomes subtle. A warp bubble isn't a tunnel or a tower. It's a carefully crafted pocket of altered geometry. Bending it backward in time would require managing enormous amounts of energy and carefully choreographing how the bubble's boundary interacts with the surrounding universe. Even a tiny misalignment, just a fraction of the curvature, could send the bubble far off course, perhaps into deep intergalactic darkness. Despite their differences, all three sketches share something important. They teach us that time is not separate from space. There is no special lever you can pull that acts on time alone. Instead, any attempt to move through time begins with shaping space in incredibly precise ways. The dance between space and time is inseparable, and every unusual configuration of one rewrites the pathways through the other. These sketches also remind us that time travel isn't an argument with the laws of physics, but a negotiation. The universe allows certain shapes and forbids others. It offers hints through wormholes, through the twisting of space-time by motion, and through the gentle bending of space itself. That time may not be a locked corridor. But it also guards its rules closely, requiring energies and materials we barely understand. In the sessions ahead, we'll explore how engineers might attempt to turn these sketches into something sturdier, and why each attempt runs into not just scientific challenges, but subtle constraints woven into the fabric of reality. For now, it's enough to hold these first images softly in mind. A tunnel, a spiral, a bubble. Three quiet promises that the flow of time may be more pliable and more mysterious than it seems. If the early sketches of time machines, wormholes, spinning towers, warp bubbles, give us a sense of what might be possible, then the next question becomes much quieter and much more intimate. How do you actually design such a thing? Not in the sense of drawing steel beams or wiring circuits, but in the deeper sense of organizing matter and energy so precisely that space-time itself begins to curve into the shapes you want. This is where the idea of building a time machine leaves the realm of imagination and steps into something stranger, architecture written directly into the universe. To see why this is difficult, it helps to picture space-time once again as a soft sheet. Every star, every planet, every particle sits on that sheet and leaves an imprint. A star presses down, making a wide, gentle basin. A planet makes a smaller dent. A black hole pushes so deeply that the sheet collapses into a funnel. And everywhere, Objects move according to these curves. Planets orbit stars, light bends around galaxies, and time itself slows near heavy masses. In this picture, designing a time machine means reshaping this sheet with incredible precision. You would need to decide exactly where the dips go, how steep they are, how far they extend, and how they shift over time. You would need to arrange matter and energy in such a way that the sheet bends into a particular pattern. Perhaps a tunnel connecting two regions, or a spiral around a spinning structure, or a compact bubble that carries a traveller through a curved path in time. But unlike a sheet of cloth, space-time does not respond to human touch. You cannot push it into place with your hands. The only tools allowed are mass, energy, and motion. A galaxy's worth of stars shapes the universe effortlessly simply by being there. But humans, working with the materials and tools we know today, can only nudge space-time very gently. Even our most powerful machines produce gravitational effects so tiny that they blend into the noise of the world. This mismatch between what is needed and what we can generate is one of the quiet truths of time machine engineering. The universe allows you to draw on its fabric, but only with pens made of gravity, light, and energy. To understand how sensitive this drawing is, imagine a quiet lake. If you toss a stone into the water, the ripples spread outward in delicate rings. Now imagine that you're trying to shape those ripples, not just one stone's disturbance, but a whole coordinated pattern of waves that must line up with perfect timing to form a single, precise shape. A tiny change in where the stone lands, or how strongly it's thrown, disrupts the entire pattern. Space-time behaves similarly. The equations that describe how mass and energy bend it are extraordinarily delicate. A small shift in energy distribution can produce large, unexpected changes in the curvature. This sensitivity creates a problem for any would-be designer. If you want to create a tunnel through space-time, the energy must be placed in exactly the right shape, a kind of gravitational sculpture where every curve supports the next. If you want a spinning structure to twist time into a loop, the density and rotation must balance in ways that leave no room for error. And if you want to make a bubble that carries a ship through folded geometry, the boundary of that bubble must be shaped and maintained with the precision of 1,000 synchronized vibrations. Even describing this mathematically requires tools we won't use here. But softly stated, the relationship between matter, energy, and curvature comes down to something like this. When energy increases in one place, the curvature deepens. When energy decreases somewhere else, the curvature lifts. The universe listens to energy as closely as a musician listens to pitch. A wrong note creates a dissonance that changes the entire composition. A gentle example helps. Think of walking on a trampoline. If someone else stands on the edge, the surface tilts slightly toward them. If two people stand at different points, the surface takes on a shape that combines both of their weights. You can predict how the surface bends by knowing where they stand and how heavy they are. But now imagine arranging hundreds of people on that trampoline, each in a carefully chosen spot, each with just the right weight, so the surface takes on a very specific shape. A ring, a tunnel, a spiral. That is closer to what engineering space-time is like. Except instead of people, you use energy. And instead of a trampoline, you use the entire universe. This analogy may feel gentle, but the real situation is even more intricate. Space-time is 4-dimensional, not 2. It curves not only in the directions you can see, but also in how moments pass. Trying to shape it precisely is like trying to sculpt an invisible wind that blows differently through every corner of the room. And yet, physics does not forbid us from trying. It simply demands precision on scales we cannot yet achieve. That brings us to the first real engineering question. If space-time can be shaped, what materials or energy sources could form the beams and columns of this invisible architecture? Ordinary matter, the kind you can hold, build, or fuse into stars, has limitations. It creates gravity that pulls inward. It creates dents, but not the upward pushes that many time machine designs require. Wormholes collapse unless held open by something that pushes back. Warp bubbles cannot form their boundary without energy that behaves differently from anything we handle in daily life. To craft the geometry needed for a time machine, you might need not only enormous amounts of energy, but energy arranged in unnatural configurations, regions where its effective density dips below the baseline of empty space, forming what we gently call negative energy. This isn't negative in the emotional sense or even in the electrical sense. It simply means that the vacuum becomes slightly less energetic than usual, allowing the curvature to lift instead of sink. Creating and sustaining such regions is an engineering challenge that borders on the poetic. You're no longer building machines from metal or composites. You're building shapes in the vacuum, structures made from the way space itself is persuaded to bend. At this stage, the idea of designing a time machine becomes less like building a vehicle and more like composing music on the universe's own instrument. An instrument that responds only to the placement and rhythm of energy. And before we look at the strange kinds of energy required to play this instrument well, we need to understand why ordinary matter cannot do the job, no matter how much of it we gather. This sets the stage for our next gentle step, where we explore the unusual, fragile, and deeply curious forms of energy that might serve as the scaffolding for tunnels through space-time. If we accept that designing a time machine means shaping space-time itself, then the next natural question is, what kind of material could hold those shapes in place? Not the physical form of the machine, the seat, the cabin, the switches, but the deeper architecture, the very scaffolding that keeps a wormhole open or stabilizes the boundaries of a warp bubble. Here, we encounter one of the strangest and most delicate ideas in physics, the possibility that to build certain kinds of space-time structures, we may need something that behaves unlike any matter we handle in ordinary life, something that doesn't just bend space-time downward, but lifts it ever so slightly upward. In familiar experience, all mass and energy pull inward. A star pulls planets toward it. A planet pulls us toward its surface. Even a small stone bends space-time, though so faintly we never notice. This inward pull is so universal that it feels like an unbreakable rule. But when physicists began studying the idea of a wormhole, a tunnel through space-time, they discovered something quietly unsettling. For a wormhole to remain open long enough for anything to pass through, the throat must somehow resist collapsing under its own gravitational pull. It must not only hold itself open, it must gently push outward, like a tent supported from inside. Ordinary matter cannot do this. No arrangement of familiar atoms or light or pressure creates an outward push strong enough to counter gravity in the right way. The equations that govern space-time, those softly phrased rules that say how curvature responds to energy, tell us that the throat of a wormhole must be filled or supported by something that, in a very specific sense, has less energy than the surrounding vacuum. It must create a local dip, not downward but upward, in the density of energy. This is what physicists refer to as negative energy. The term may sound dramatic, but it simply means this. Imagine the baseline energy of empty space as a quiet lake at rest. Ordinary matter is like a stone dropped into the lake. It creates a depression. Negative energy would be the opposite. A small, localized mound rising above the calm water, a gentle upward push instead of a downward pull. If a throat of a wormhole sits in such a region, that upward push helps hold it open, preventing the tunnel from collapsing. But how can space have less energy than empty space? The answer lies in the strange, vibrating world of quantum fields, the realm where particles appear and disappear, like fleeting ripples that the vacuum itself produces. Even at perfect stillness, the vacuum buzzes with tiny fluctuations. In some very specific arrangements, those fluctuations behave differently in one region than in another, creating a small energy difference. One of the simplest examples is the Casimir effect, which arises when you place two metal plates extremely close together. The quantum fluctuations between the plates are slightly restricted compared to those outside the plates, creating a tiny imbalance. The plates feel a gentle push toward each other. This push can be interpreted as the vacuum between them having slightly less energy, effectively a small pocket of negative energy. This effect is real and measurable, but incredibly small. To support even a microscopic wormhole, you might need negative energy densities far greater than anything produced in a laboratory. Imagine trying to inflate a vast invisible bubble with a substance you can currently create only in the thinnest film. The contrast between what theory requires and what our tools can generate is immense. Still, the existence of even this faint whisper of negative energy is important. It tells us the universe does allow such behavior, at least in principle. It means the idea is not pure fantasy. Something in nature can produce regions of energy that behave opposite to our expectations. This small door opened by quantum mechanics has inspired physicists to imagine ways of amplifying, shaping, or sustaining these pockets on larger scales. One possibility is that negative energy might appear naturally in certain extreme environments, near black holes, within strong electromagnetic fields, or in configurations of fields we have yet to understand fully. But even the most optimistic scenario suggests that stabilizing a wormhole big enough to send even a message through, let alone a human traveler, would require orchestrating vast amounts of this unusual energy with extraordinary precision. To see why such precision matters, imagine trying to balance a pencil on its point. A slight movement sends it falling. A wormhole is something like that pencil, but far more fragile. Its stability depends on exactly the right distribution of energy. Too little outward push and the throat collapses, too much and it buckles outward uncontrollably. The slightest asymmetry may cause the structure to tear or twist into unpredictable shapes, possibly ending in a singularity, a place where the curvature becomes so extreme that our equations lose meaning. Similarly, a warp bubble, the kind of structure that could carry a traveller by shifting space in front and behind, needs a boundary where energy density changes rapidly, almost like a steep cliff in the fabric of space-time. If that boundary is not maintained exactly, the bubble cannot hold its shape. The math behind these structures, when translated softly, tells us that each curve, each change in curvature, depends entirely on how energy is arranged, and this arrangement must be precise not on human scales, like millimeters or micrometers, but on scales where even tiny fluctuations of quantum fields matter. What does all of this mean for our attempt to design a time machine? It means that if wormholes or warp bubbles are part of that design, the first requirement is an ingredient we barely know how to handle: negative energy shaped and held steady, not for a moment, but for as long as the traveller needs. It means designing containers that hold not material, but vacuum itself reshaped into a specific pattern. It means controlling not just mass or light, but the background hum of the universe's own quantum fabric. This may sound discouraging, but there is wonder in it too. For the first time in human history, we can describe the kind of material that might hold open a tunnel through space-time. We've glimpsed, through quiet quantum experiments, hints of how the vacuum behaves. We've learned that time and space are far more flexible than intuition suggests. And while the road to engineering such structures is long and uncertain, the very act of imagining them brings us closer to understanding the deep architecture of the universe. In the next step of our journey, we'll explore how these delicate ingredients interact with the idea of creating a bubble or pocket of space-time, something local, contained, and shaped with care, without disturbing the vast cosmos around it. If wormholes are like tunnels dug through the fabric of space-time, then warp bubbles are more like gentle folds, small, contained regions where the universe behaves differently for a moment. Instead of carving a passage between distant places, a warp bubble tries to carry a traveller by reshaping the space directly around them. In stories, this idea often appears as a ship darting faster than light, leaving a shimmering distortion in its wake. But the actual concept is much quieter and more subtle. It begins with an image, a boat floating on a perfectly calm lake, carried forward not by its own motion, but by a slow, steady wave beneath it. Inside a warp bubble, the traveller sits in a patch of space that feels perfectly ordinary. They aren't crushed by acceleration, stretched by gravity, or exposed to strange radiation. To them, the bubble feels like a soft pocket of stillness. The bubble's boundary, its thin shell where space contracts in front and expands behind, does all the work. It's this shifting of space, not the movement of the ship, that allows the bubble to drift. The idea hinges on something subtle but important. Nothing inside the bubble breaks the cosmic rule that nothing can move faster than light. Instead, the bubble itself moves because the space around it changes shape. Space isn't a fixed stage with rigid dimensions. It can stretch and compress. When distant galaxies rush away from us faster than light, they aren't moving through space that quickly. Space itself is expanding. The bubble borrows this idea, but in a much more focused and controlled way. To imagine the engineering behind this, picture a small dome floating above a sheet of soft fabric. If you gently push down on the fabric behind the dome and lift it slightly ahead, the dome glides forward. Not because it slides, but because the fabric beneath it shifts. This is the essence of a warp bubble: compressed space ahead, expanded space behind. The bubble moves because the landscape moves. This makes warp bubbles deeply attractive as a concept. Unlike wormholes, which require a stable tunnel between two mouths, a warp bubble is self-contained. It doesn't need two openings. It doesn't require synchronizing distant regions of space-time. It's just one region made to behave differently for as long as the bubble is active. For a time machine, this simplicity seems promising. If you could make a bubble follow a curved path in space-time, perhaps bending backward into an earlier moment, then the traveller inside might emerge in a different time without ever leaving the safety of the bubble's interior. But even this gentler picture hides enormous challenges. The first is energy. While warp bubbles don't need wormhole-like tunnels, they still require vast amounts of energy to sculpt their boundaries. The shape of the bubble depends on how sharply space is compressed or expanded across its thin shell. These gradients, these sudden changes in the curvature of space-time, demand energy densities far beyond anything we can produce. And just like wormholes, warp bubbles seem to require regions of negative energy, those fragile pockets where the vacuum dips ever so slightly below its usual level. Inside a warp bubble, the traveller feels nothing unusual, but outside the bubble's wall, the curvature must change rapidly. You can picture this as a cliff in the fabric of space-time, a place where the universe changes direction sharply. The bubble's wall must hold this shape steady, resisting collapse or expansion. This is not like holding open a tunnel, it's like maintaining a delicate sculpture made of invisible wind. If the bubble's boundary wavers, if one side becomes slightly too steep or too shallow, the entire bubble can lose cohesion. A second challenge is local versus global distortion. A warp bubble aims to be small and contained, affecting only the region immediately around it. But space-time does not come with tidy boundaries. If you push space here, something shifts there. The universe responds to changes in energy and curvature with a sensitivity that allows no shortcuts. Even a bubble designed to be small could send subtle ripples outward, influencing regions far beyond its intended boundaries. A poorly shaped bubble might disturb or destabilize distant paths of light or gravity in ways that accumulate over time. Imagine trying to create a whirlpool in a bathtub without disrupting the far corner of the water. No matter how gentle your motions, ripples spread. Space-time, though more complex, behaves similarly. Every attempt to localize an effect risks producing global responses. Designing a warp bubble means crafting a region that is sharply defined, yet isolated from the broader universe, a contradiction that requires incredible precision. The third challenge involves navigation. Even if you could form the bubble and keep it stable, steering it would be far more delicate than piloting a ship or an aircraft. You wouldn't be navigating through space. You'd be navigating through space-time itself. The bubble must follow a carefully plotted path, gently curving through the geometry you've sculpted. A tiny miscalculation in the shape of the bubble or the distribution of energy could send it drifting into deep interstellar space, or toward a region where gravitational forces tear it apart. Imagine trying to aim a soap bubble through a forest during a breeze. The bubble feels stable from within, but every subtle external influence shapes its path. And if the bubble were intended not just to travel through space, but to follow a trajectory that loops into the past, the level of precision would become almost unimaginable. You'd need to match not only the location of past events, but their timing down to incredibly fine scales. Even arriving a fraction of a second early or late might place you in a completely different moment, and because space-time curves differently near stars, planets, and even dense clouds of interstellar matter, the bubble must navigate a terrain that is constantly shifting. All of this brings us to a quiet truth. Warp bubbles are beautiful as an idea because they let us imagine time travel without needing vast tunnels or infinite structures. But their elegance hides the same underlying difficulty that troubles all time machine designs: the need to rearrange energy in ways that stretch our understanding of physics. The bubble asks for smooth boundaries, negative energy, and perfect guidance. It asks for geometry we do not yet know how to carve. Still, the fact that we can describe such things at all is remarkable. It means that the universe, at least in theory, whispers possibilities. It offers images of boats riding waves of space, of gentle folds that carry travellers through a landscape that changes shape around them. Whether these images will ever become engineering remains unknown, but they give us a foundation for imagining the next step. How to gather the energy needed to sculpt such forms, and how to coax strange materials into behaving like the beams and supports of a machine built not from matter, but from the deep structure of space-time itself. When we follow this path a little farther, we find ourselves standing at the edge of an extraordinary question. What kind of power source could feed such a machine, and how would we keep that power under control? That is where our journey drifts next. When science fiction imagines a time machine powering up, the moment always arrives with a burst of drama. A lever is pulled, a glowing switch is slapped, a sudden hum fills the air as the machine wakes like some ancient creature stretching after centuries asleep. It makes intuitive sense. Big adventures deserve big sound effects. But if we take the idea seriously, if we imagine not a fictional time machine but a real one shaped by the rules of the universe, that comforting click and whoosh becomes wildly insufficient. In reality, the machine wouldn't just ask for a jolt of electricity. It would ask for the kind of power that stars release simply by shining, and not just a momentary flash, but perhaps steady streams of energy, collected, stored, and shaped with impossible precision. A gentle way to begin thinking about this is to compare different scales of power, one by one, in a way the mind can hold. A household light bulb uses a handful of watts, a tiny sip from the electrical grid. A typical home might draw thousands of watts when everything hums together. A bustling city pulls billions. A rocket launch, pushing tons of metal against Earth gravity, gulps down energy at a rate that dwarfs an entire metropolitan district. And yet, even these enormous human achievements are small flickers compared to a star like the Sun, which pours out more energy every second than humanity has consumed in all of history. It helps to imagine the Sun as a quiet, patient lighthouse in the sky, releasing a steady beam of light and warmth in every direction. The total energy radiated every second is almost beyond imagining. If we gathered all the electricity used by every device, every home, every factory on Earth, we would still be tapping only a vanishingly tiny fraction of the Sun's output, something like a grain of sand compared to an entire beach. And when physicists sketch the energy budgets for things like wormholes or warp bubbles, those equations whisper an uncomfortable truth. Even 1 second of stellar output might barely be enough to shift space-time in the way a time machine requires. This is because bending space-time is not a mild activity. It demands not just energy, but energy arranged in densities and patterns far beyond anything our engines or lasers or particle accelerators can currently provide. The gentle depressions created by planets and stars are results of their mass energy content, a kind of gravitational weight that shapes the universe around them. To sculpt space-time into a tunnel or bubble or loop, we must create patterns of curvature so deep or so steep that everyday matter simply cannot supply the needed force. It would be like trying to carve a canyon using only a spoon. The tool and the goal exist in different worlds. To make this challenge feel a little less abstract, imagine wanting to power a machine by plugging it into the wall. The energy trickles in from faraway generators, through wires and transformers, until it reaches the device. Now imagine plugging that device not into a wall, but into a star, not metaphorically but literally, capturing a significant fraction of the star's light and feeding it into the machinery that shapes space-time. This is the realm where ideas like a Dyson swarm appear, not a single massive shell around a star, but a vast cloud of orbiting collectors, each sipping starlight and converting it into usable energy. It's a thought experiment, but one grounded in gentle logic. If a time machine requires the energy of a star, then one must first learn how to harvest a star. The Dyson swarm is appealing because it feels almost practical in a distant future sense. Each collector, imagined as a thin, mirror-like satellite, gathers sunlight and beams it to a central hub. Over time, the swarm thickens, absorbing more and more of the star's output. It is the cosmic equivalent of placing thousands of hands beneath a waterfall to catch every drop. And while the idea remains purely theoretical today, it offers a sense of scale. The power to bend space-time might demand the luminosity of an entire sun. But gathering power is only one piece of the puzzle. The second is using that power efficiently. Every joule that slips away as heat, light, or stray vibration is lost potential, energy not available to shift space-time. A time machine cannot simply waste energy the way our machines do now. Cars leak heat. Rockets produce enormous flames. Computers radiate warmth. Even stars waste energy in every direction. A time machine would need to operate almost perfectly. Nearly all the energy gathered must be transformed into carefully sculpted curvature. The efficiency required might be unlike anything we currently understand, so close to perfect that even small losses could doom the entire structure. This leads to what you might call the efficiency paradox. To create a time machine, you need colossal amounts of energy. But the more energy you need, the harder it becomes to store, control, and use it without losing most of it in the process. Even if a civilization learned to gather starlight on massive scales, it would still need devices to funnel that energy into space-time in exactly the right shapes. Those devices must be stable, precise, and resistant to catastrophic failure. Imagine trying to pour an ocean through a straw without spilling a drop. The difficulty isn't just in acquiring the water, it's in guiding the flow. Another way to picture this is through a kind of cosmic campfire. If you throw wood into a fire, you get heat and light. But if you need the flame to do something extraordinarily delicate, like melt a single grain of sand into a perfect drop of glass, you must control the fire's shape, temperature, and direction. A time machine must control energy in that same spirit, but on a scale where the fire is as bright and powerful as a star. This brings us to a quiet realization. The engine of a real-time machine might not be a machine at all in the usual sense. It wouldn't be something you store in a garage or bolt together from components. Instead, it might be a system the size of a solar system, a set of structures orbiting a star, collecting its light, funneling it inward, and shaping that light into the specific patterns needed. The control room, the place where the traveller sits, might be the smallest part of the device. The true machine would be the star-powered architecture surrounding it. And yet, even with energy on stellar scales, another challenge remains: finding, shaping, and controlling negative energy, the strange fuel that holds wormholes open or defines the boundaries of warp bubbles. Gathering power from a star is already immense, but conjuring and taming something as fragile as negative energy is a challenge all its own, one that makes even Dyson-level engineering feel almost simple in comparison. It is here, at the edge of what seems possible, that the path gently shifts toward the next question. If the universe allows negative energy in small, fleeting pockets, how might we collect it, shape it, and keep it calm? And could the very act of trying to hold it steady threaten the fabric we're trying to sculpt? These are the mysteries waiting in the next part of our quiet exploration. If ordinary energy behaves like a sturdy rope pulling space-time inward, then negative energy behaves like a whisper of wind pushing outward, lifting the fabric ever so slightly. It is not energy in the familiar sense, no flame, no spark, no glow, but a subtle imbalance in the quantum vacuum, something that exists in rare and delicate forms, always fleeting, always difficult to shape. And yet, for wormholes, warp bubbles, or any exotic structure that bends time in dramatic ways, this whisper may be the most important ingredient. It is the thread that holds open the tunnel, the boundary that defines the bubble, the secret force that keeps the geometry from collapsing inward. But if this ingredient is essential, it is also deeply unruly. Trying to contain negative energy is a bit like trying to bottle a shadow, or hold on to the coolness that lingers after a breeze. It slips, shifts, and reacts to the world in unexpected ways. Shaping it requires a level of control we barely understand, and stabilizing it might be as difficult as finding it in the first place. One way to begin is with a quiet image. Imagine two metal plates placed extremely close together in a vacuum. Between them, quantum fluctuations, the tiny restless ripples that fill all of empty space, are slightly suppressed. Outside the plates, the fluctuations dance freely. Inside, the dance is constrained. This imbalance creates a gentle force pushing the plates together. It is a real effect, measurable in laboratories, and one of the simplest hints that negative energy can exist. Not as a glowing substance, but as a subtle dip in the energy of the vacuum, lower than what nothing normally holds. This phenomenon, known softly as the Casimir effect, is one of the rare windows into the universe's ability to produce negative energy naturally. But the amount produced is incredibly small, far too small to hold open even a microscopic wormhole throat. It's like discovering that a breeze can flicker a match and then trying to use that breeze to push a ship across the ocean. If we imagine scaling up this effect, stretching the tiny dip in vacuum energy into a vast region where space-time is nudged outward, we begin to see the engineering nightmare that follows. Negative energy is not something that accumulates easily. It doesn't pile up like coal in a furnace or compress like fuel in a tank. It behaves more like a pattern than a substance, a shape in the quantum fields that must be coaxed into existence with extreme care. To keep that pattern stable, we would need something like a containment vessel for vacuum itself. This is a difficult concept to picture, but imagine building a room not to hold material objects, but to hold the absence of them. Imagine creating walls, not of metal or ceramic, but of electromagnetic fields or quantum configurations that persuade the vacuum inside to behave differently than the vacuum outside. The container is not holding a fluid or a gas, it is holding a pattern in the structure of space. Such a container must meet impossible demands. It must not leak, meaning the negative energy must not spread or decay into normal vacuum. It must not fluctuate, because small oscillations could cause the geometry to wobble or collapse. And it must not interact too strongly with normal matter, because ordinary atoms respond dramatically to extreme curvature. Place a piece of matter too close to a region of strong negative energy, and its particles might stretch, tear, or fall into chaotic states. Imagine trying to store liquid helium in a container that melts at room temperature, or trying to hold antimatter in a jar that it instantly annihilates. These comparisons give only the faintest sense of the challenge. Negative energy is more ephemeral, more sensitive, and far more deeply rooted in the quantum fabric than any material substance we know. Now picture adding this delicate fuel to a time machine. The region of negative energy must be shaped into a specific form, not a random dip in vacuum energy, but a carefully sculpted field that matches the desired geometry. For a wormhole, the outward push must be balanced along the throat, strong enough to resist collapse but not so strong that it destabilizes the tunnel. Like holding a tent open in a windstorm, too much pressure and the structure buckles, too little and it falls inward. For a warp bubble, the boundary is even more complex. The region ahead of the bubble must compress space, while the region behind must expand it. Both processes require negative energy in different patterns. The bubble's wall becomes a thin, fragile shell where the universe transitions sharply from one mode to another. Even slight imperfections in this shell, like the uneven edge of a soap bubble, could tear the bubble apart or cause it to drift unpredictably. This brings us to the idea of feedback control, a concept familiar from engineering but far more delicate when applied to space-time. Instead of measuring voltage, temperature, or pressure, the system would need to sense the curvature of space-time itself. It would need to read the subtle ripples of energy density and adjust its fields in response, strengthening the negative energy here, softening it there, smoothing out any distortions that might grow unstable. You can imagine a kind of quiet dance, the machine constantly listening to the geometry it creates, adjusting its patterns the way a musician adjusts the tuning of a string. Micro changes made continuously, keeping every curve just right. The slightest delay or miscalculation could allow instabilities to grow. In extreme cases, the region of negative energy could expand uncontrollably, collapse quickly, or generate bursts of high curvature that ripple outward, disturbing nearby space. There's an irony here. Even if we learn to gather negative energy and shape it, keeping it calm might be harder than finding it. The vacuum wants to return to its default state. The universe dislikes these unusual configurations, or at least treats them as precarious. Holding a region of negative energy steady would be like balancing a tower of glass rods on a breeze. Technically possible, but requiring reflexes and precision far beyond anything we currently possess. And yet, the very delicacy of this idea makes it beautiful. It suggests that a time machine, if it exists one day, won't be a brutal device powered by raw force. It will be something more like an instrument, a finely tuned orchestra of fields and energies, coaxing the universe into new shapes with a touch so gentle it borders on the poetic. As we continue our journey, it becomes clear that the challenges of energy and exotic matter don't exist in isolation. They touch something even more fundamental, the question of whether the universe allows such structures at all, and if it does, whether it also guards itself with quiet rules meant to keep its history intact. That is where we drift next, toward paradoxes and the elegant defences that may lie woven into the fabric of time itself. If designing a time machine were merely a question of energy and engineering, the task would already be monumental. But time travel carries another kind of difficulty, one not born from physics, but from logic itself. Even if we could sculpt space-time into a loop, even if we could stabilise wormholes or warp bubbles and feed them with stellar power, we would still face the quiet riddle at the heart of every time travel story. What happens when cause and effect begin to twist around each other? A gentle way to approach this is through a simple, old-fashioned paradox, the grandparent paradox. It's usually told with a humorous edge, the kind of riddle you might whisper at a campfire. Imagine someone using a time machine to travel into the past, arriving decades before they were born, and preventing their grandparents from meeting. If that happened, the traveller would never be born. But if they were never born, then how did they travel back in time? And if they never travel back in time, then the grandparents would meet after all, and the traveller would be born again. This looping contradiction is uncomfortable not because it defies physics, but because it defies meaning. It's like writing a sentence where the end erases the beginning. The universe, which seems so consistent and orderly, cannot host a story where events contradict themselves. So the question becomes, if time travel were possible, how would the universe prevent such contradictions? Physicists and philosophers have offered two broad answers, each softly elegant in its own way. The first is the idea of self-consistency. In this view, the universe allows time loops, but only if everything that happens within them fits together without contradiction. If you go back in time, your actions were always part of history. You may try to prevent your grandparents from meeting, but events would unfold in such a way that your attempt fails, or succeeds in a way that still leads to your birth. Maybe you distract one of them briefly, but they meet later. Maybe your presence influences events gently, but never enough to break the continuity of your own existence. This idea treats time not as a free landscape to sculpt at will, but as a tapestry already woven, where loops must align with the threads that already exist. The second answer is sometimes called the many branches view. In this perspective, every time you make a change in the past, the universe quietly opens a new path, a new branch of reality, where your actions become part of its story. In the original branch, where your grandparents met without interference, your birth still happens. But in the branch you create by travelling back, the story unfolds differently. You do not erase your original timeline, you simply step into another. It's not contradiction, but multiplication, a soft blossoming of possibilities rather than a break in cause and effect. Both answers avoid paradoxes, but they paint very different pictures. One keeps the universe tightly coherent, gently steering events toward consistency. The other treats reality like a tree with infinitely branching limbs, each limb a world where different choices play out. We don't yet know which, if either, truly reflects the underlying nature of time, but both offer ways for loops to avoid logical knots. And this brings us to an engineering question as curious as it is unsettling. If we built a time machine, would it come with rules? Would the geometry itself refuse certain trips guiding the traveller, away from contradictions? Would the machine's internal guidance system lock out destinations that lead to paradox? It's not hard to imagine a device where attempts to reach certain coordinates in time simply fail, either because the geometry collapses when pushed too far, or because the feedback systems that keep the wormhole or bubble stable cannot maintain shape when paradox looms. Think of it as trying to walk against a strong wind. You can lean forward, push harder, try different angles, but no matter what, the wind pushes you back. A time machine designed within the universe's rules might push back in similar ways. The closer you get to a paradoxical path, the more unstable the geometry becomes, until the machine simply cannot take you further. In the self-consistency view, this resistance would be woven into physics itself. In the many branches view, the machine might not resist, but you would enter a branch where the paradox dissolves harmlessly. Another gentle way to imagine this is through the notion of causal pathways, the invisible lines connecting cause to effect. When you move forward in time, these pathways are smooth and predictable, but when you try to move backward, the pathways may become tangled, like threads pulled too tightly. A time machine might sense this tension, not through mysticism, but through the very curvature of spacetime, and adjust its trajectory to avoid the knots. What looks like logic becoming confused might actually be geometry resisting a shape that cannot coexist with itself. These ideas might seem abstract, but they remind us that paradoxes are not merely puzzles for storytellers. They are clues pointing toward deep rules in the universe. Whether time loops are allowed or forbidden depends not just on energy or curvature, but on how the universe chooses to preserve meaning. And that preservation, soft and subtle, may be one of the strongest defences against runaway time travel. Of course, logic alone cannot settle the matter. To understand how paradoxes truly behave, we must shrink our attention to the smallest scales, where particles slip into superpositions and probabilities shimmer like heat over pavement. The quantum world handles time very differently from the classical one, and in that domain, loops and contradictions may follow an entirely new set of rules. Before we drift into those quantum depths, though, it's worth sitting with this quiet realization. Designing a time machine is not only about bending physics, it's about bending stories. It asks what kinds of narratives the universe allows, and which ones it quietly refuses. And in that refusal, or acceptance, we begin to glimpse the boundary between possibility and impossibility, not drawn in ink but woven into time's own fabric. That boundary becomes even clearer when we watch what happens at the smallest scales, where time loops behave less like contradictions and more like delicate negotiations. That is, the path ahead. When we descend into the world of the very small, the rules of reality soften. Things that seem impossible at human scales, objects being in two places at once, particles choosing paths only when we look at them, events unfolding like probabilities instead of certainties, become entirely ordinary. This is the quantum realm, where intuition wavers and the universe whispers in riddles. If time travel invites paradoxes in the everyday world, then perhaps the quantum world can teach us how those paradoxes are negotiated, dissolved, or gently sidestepped. A calm way to begin is with a small image. Picture a tiny coin resting on your fingertip. In the classical world, that coin is always either heads or tails, but in the quantum world, the coin can rest in a state that is softly both, heads and tails overlapping until someone observes it. This idea, called superposition, isn't mystical. It's simply the universe allowing possibilities to coexist until some event forces a choice. Now imagine sending this tiny quantum coin through a loop in time. What happens to the overlapping possibilities? Does the coin return to its past in both states? Does it interfere with itself? Does it collapse into one outcome? Physicists have explored these questions for decades, not with literal coins, but with particles and mathematical models that mimic what a time loop might do to them. One approach, described without any symbols, is known gently as the self-consistency condition. In this picture, whatever travels around the loop must return in a state that fits with the state it had before entering the loop. It's a kind of quantum negotiation. The universe checks the incoming state, checks the outgoing state, and settles on the version that keeps the story coherent. If the particle tries to return in a contradictory state, the loop simply does not stabilize. The system adjusts until everything lines up. It's like a musical phrase repeating over and over until the notes fit into a clean, harmonious cycle. This kind of model suggests that quantum systems naturally avoid paradoxes by choosing outcomes that keep the loop consistent. If you imagine a particle poised between two choices, heads or tails, the loop nudges it toward the choice that ensures the past and future align. Nothing magical happens. The system just obeys a rule requiring that its evolution makes sense when traced in a circle. But there is another, stranger family of models where loops do not insist on such tidy agreements. In these scenarios, the quantum state inside the loop can influence itself in non-linear ways, meaning small differences can snowball into dramatic changes. Some versions of these models allow a time loop to perform feats of computation that seem impossible under ordinary quantum rules. Problems that might take billions of years to solve could be settled instantly by a system that loops a potential answer back to itself, refining the outcome again and again until consistency is reached. This is where quantum time loops begin to resemble a problem-solving device. Imagine a puzzle where each attempt feeds into the next, the loop refining possibilities until it lands on a solution. A time machine interacting with quantum systems might behave similarly, not because it wants to compute anything, but because the geometry of the loop enforces repeated interactions. Each pass through the loop updates the state, and the system settles into whatever version satisfies the geometry. But this computational dream comes with a quiet warning. Nonlinear behavior in physics is notoriously sensitive. Slight changes, tiny nudges, minuscule fluctuations can explode into drastic differences. In everyday life, this is what people call the butterfly effect, where small events ripple outward unpredictably. In a time loop where states feed back into themselves, the sensitivity could be extreme. A particle's quantum state might spiral into instability. A slight deviation could make the loop collapse or, worse, amplify itself to the point of destroying the consistency needed for the loop to exist. This sensitivity suggests that a time machine is not merely an engine for shaping geometry. It is also a device that must carefully manage quantum interactions. The hardware of the machine, the fields, the energies, the curvature, may be difficult enough to build, but the software, meaning the quantum behavior inside and around the machine, may be even more delicate. Every particle that passes through the machine, every photon bouncing around inside the bubble or tunnel, becomes part of the negotiation between past and future. A poorly controlled quantum environment could create chaotic feedback loops, like whispers echoing endlessly in a chamber until the chamber shakes itself apart. To imagine this, picture a room filled with mirrors, each reflecting light back and forth. A single beam, if aligned just right, might bounce forever. But if one mirror tilts slightly, the beam scatters and the stable pattern collapses. A time loop is like a room full of quantum mirrors. Every interaction has to align perfectly with the geometry of the loop. Every particle must behave in ways that don't disrupt consistency. And the larger the machine, the more particles are involved, each one a small vote in the negotiation of the loop. This is why physicists sometimes say that time travel, if it exists, is likely to be self-regulating. The quantum world may help maintain logical coherence by nudging systems towards stable outcomes, but it may also prevent loops from forming if the conditions become too unstable. Some theories even hint that when a region of spacetime tries to form a closed loop, the quantum vacuum becomes restless, throwing fluctuations into the loop that destabilize it. It's as if the smallest constituents of the universe carry their own sense of order, gently pushing back against structures that violate the deeper rules of causality. And yet, despite all of this complexity, the quantum perspective offers something comforting. It suggests that paradoxes are not inevitable. The universe has subtle ways of smoothing out contradictions, of choosing paths that keep stories coherent, of allowing possibilities to overlap without falling into chaos. Time loops in the quantum realm are not logical disasters. They are delicate negotiations, tiny dances of probability shaping themselves into consistency. As we return from this microscopic landscape, we carry with us a new understanding. The time travel is not just a geometric problem or a matter of raw power. It is a conversation between levels of reality, between the smooth curves of space-time and the shimmering probabilities of quantum behavior. And in that conversation, there may be an unseen guardian, a kind of quiet protection woven into the laws of physics themselves. That guardian takes clearer shape when we listen to the warnings of a thinker who spent his life watching the boundaries between possibility and impossibility, Stephen Hawking. His gentle, teasing idea of a universal chronology protection agency awaits us next. When people imagined Stephen Hawking speaking about time travel, they often pictured him surrounded by chalkboards full of symbols, weaving dense equations into elegant arguments. And while he certainly did that, he also had a gift for wrapping deep ideas in soft humour. One of his most memorable jokes was the suggestion that the universe might have its own chronology protection agency, an invisible guardian ensuring that time runs forward in a sensible way. It was a playful image, a cosmic department of time security. But beneath the humour lay a profound physical insight. The laws of nature may gently prevent time machines from ever fully forming. To understand this idea, it helps to remember that time travel in physics is tied to a very specific structure, a loop in space-time, a path you can walk that brings you back to a moment you've already lived. These loops, spoken of softly as closed paths through time, appear in certain mathematical solutions to Einstein's ideas about gravity. That means, on paper, the universe allows them. But when we look closer, something curious happens. As a region of space-time begins to twist or fold into a loop, the quantum vacuum surrounding that region begins to react. The vacuum is not empty. Even in perfect darkness, space hums with tiny fluctuations. Particles flicker into existence and fade again, like sparks that never quite catch fire. These fluctuations are usually so small that they have no noticeable effect. But as the geometry of space-time stretches or curves toward a time loop, something strange occurs. Those tiny fluctuations begin to amplify. The vacuum starts to fill with restless energy. It is as though the universe feels the fabric being folded back onto itself and begins to resist. To picture this in a gentle way, Imagine a thin sheet of warm wax. If you try to bend it slightly, it will bend without struggle, but if you try to fold it all the way back until two parts of it touch, the wax wrinkles, softens, and begins to tear. It reacts to the stress long before the fold is complete. The quantum vacuum in Hawking's vision behaves a little like that sheet, quietly opposing any attempt to create loops that would allow cause and effect to collide. The technical reason for this has to do with the energy that quantum fluctuations generate near the boundary where a loop is about to form. If you were to track these fluctuations carefully, you would find that their contribution to the energy of the region increases dramatically as the geometry tightens. In simple language, the vacuum becomes extremely energetic, as if resisting the attempt to close the loop. Ultimately, this energy may rise so sharply that it overwhelms whatever structure is being built, destabilizing the entire configuration. If a wormhole throat were being stretched into a time-shifted passage, these quantum effects might cause the walls to vibrate, collapse, or flood with radiation. If a warp bubble were trying to curl backward into an earlier moment, the bubble's boundary might tear or flare into intense light. If a spinning tower were trying to twist space-time into a spiral of returning moments, the field around it might erupt with unpredictable bursts of energy. These are not explosions in the cinematic sense, but natural responses from the fabric of reality. Small warnings that grow louder as the geometry approaches the forbidden shape. This is the essence of Hawking's chronology protection idea. The universe may allow you to bend space-time, distort it, and slow time to a crawl, but it quietly forbids you from folding it into a loop that permits paradox. It's not a rule written in cosmic stone, it's more like a tendency woven into the equations themselves. When cause and effect begin to blur, the fluctuations of the vacuum rise like a tide, gently but firmly sweeping away the fragile structure before the loop can complete. This does not mean time travel is impossible in all forms. Travelling into the future through time dilation, a natural effect of high speed or strong gravity, is fully allowed. The universe doesn't object. If you orbit a black hole or accelerate close to the speed of light, your personal moments will pass more slowly than those far away, and you'll glide forward into the future. That kind of time travel doesn't threaten cause and effect, it simply stretches the river of time in a different way. But travelling into the past or creating a loop that leads back to your own history touches something deeper. It invites contradictions. It asks the universe to rewrite its own story. Hawking's insight was that the universe might have defences against that. Not conscious defences, not moral defences, but physical ones. To make this feel less abstract, imagine a traveller approaching a region where a time loop almost forms. The closer they get, the more the surrounding vacuum fills with energy, like fog becoming gradually thicker. Instruments begin to detect unpredictably rising radiation. The field becomes noisy, unstable. The closer they move, the more difficult it becomes to keep the machine's geometry intact. It's not that the universe refuses access, it simply becomes impossible to maintain the structure that leads to paradox. This has a gentle elegance. It suggests that the universe is already self-guarding, not in a dramatic or punitive sense, but the way a healthy body resists infections. Loops that threaten causality self-destruct through perfectly ordinary physics. It's not magic, it's the natural shape of the laws we live within. And yet, Hawking's idea does not close the door on all exotic geometries. Wormholes might exist in distant regions of the cosmos stabilised by unknown physics. Warp bubbles might be possible in forms that never curl backward in time. Even closed loops might form microscopically, appearing and disappearing too quickly to cause trouble. The universe may allow hints of possibility, but step in only when those possibilities jeopardize the consistency of its history. From an engineering perspective, This means that solving the paradox problem is not only a matter of logic or software. The machine itself may need to detect rising vacuum fluctuations, sense when a trajectory approaches the dangerous boundary, and redirect its curvature before the universe slams the door. The machine becomes a partner with physics, not a conqueror of it. The paradoxes, in this sense, are not simply intellectual problems. They are warnings, soft, persistent reminders that time is not just a dimension to be manipulated, but a story to be preserved. And in the dance between possibility and protection, between geometry and quantum resistance, we find ourselves at the threshold of another kind of challenge. Whether a human body, a human mind, and a human sense of self can even endure the distortions a time machine would impose. This brings us gently into the next chapter of our journey, where engineering meets biology, and where the question shifts from can we build it to could we survive it? When we imagine time travel, we often picture the machine first, the glowing rings, the soft hum of power, the shifting lights that signal the beginning of a journey beyond the ordinary. But rarely do we pause to consider the passenger. What happens to a human body, made of fragile bones and soft tissues and delicate rhythms, when it is placed inside a region where space-time itself bends, stretches, or changes tempo? What happens to a person who is asked not only to move through space, but through time at speeds or in directions the body was never designed to experience? A gentle place to begin is with something familiar: acceleration. If you have ridden in a fast car or felt the upward push of an airplane taking off, you've experienced a tiny sample of what physicists call G-forces. When a vehicle changes speed suddenly, your body notices. Your muscles strain, your blood shifts, and for a moment you feel heavier. This is because your body prefers to move in a straight line. When something forces it to change direction, you feel the result as pressure. But the forces involved in time travel scenarios, high acceleration, rapid changes in velocity, or extreme gravity, could be far greater than anything we encounter in daily life. A spacecraft trying to skim the edge of a black hole to gain time dilation, for example, would experience gravitational gradients so sharp that different parts of the body would feel different pulls. This is the gentle name for something far more dramatic: tidal forces. These forces stretch and squeeze not because space is being mean, but because gravity changes from one location to the next. Even small differences can affect blood flow, organ stability, and the skeletal frame. If a time machine relied on extreme acceleration to create time dilation, something close to the speed of light, your body would endure intense stress. Imagine going from 0 to orbital speed in a split second. Even if the machine cushioned the acceleration with soft suspension fields or gradual build-up, your cardiovascular system would still need to adapt. Blood might rush toward your hands or feet. Your chest might feel heavy, as if the air inside it suddenly thickened. Pilots train for such forces, learning to tense muscles in specific ways to keep blood from draining out of their heads. But even they cannot tolerate extremely high accelerations for long. On the other extreme lie regions of strong curvature, places where space-time bends steeply. If a wormhole throat or warp bubble wall is shaped incorrectly, sharp variations in curvature might interact with the body in unpredictable ways. Your body is made of countless tiny particles, each following its own gentle path through space-time. If those paths diverge too quickly, if space-time pulls your feet slightly faster than your head, or twists your torso in ways your spine cannot follow, the sensation might be disorienting, painful, or worse. Engineers designing such machines would need to ensure that the interior region remains flat and calm, a quiet bubble of ordinary physics protected from the turbulence outside. Radiation is another quiet danger. regions near high curvature, around black holes near rapidly accelerated frames, or inside unstable warp bubbles, often overflow with high-energy particles. These particles can slice through cells, disrupt DNA, or overload the body's natural repair systems. Astronauts already face increased radiation during spaceflight, and time machines, if not designed carefully, could magnify these risks. Any responsible design would need shielding, not metal plates, but fields and geometries that deflect or absorb dangerous particles before they reach the traveller. Beyond these physical stresses lies something subtler, the slow effect of time dilation on living tissue. If time passes differently for you than it does for the world outside, your cells age at a different rhythm. Your heart beats through minutes while years pass for others. This might seem harmless. After all, your body isn't aware of the outside world's clock, but we don't yet know how biological systems respond to long periods of slowed aging. Do circadian rhythms drift? Do repair processes accelerate or slow? Does immune response behave differently? These questions rest at the intersection of physics and medicine, a place we have barely begun to explore. And then there is the possibility, however theoretical, that abrupt changes in the flow of time might affect the coherence of cellular processes. Many biological functions rely on precise timing, the opening of ion channels in neurons, controlled duplication of DNA, the synchronized contraction of muscle fibers. If a person was suddenly shifted into an environment where time stretched or compressed, even slightly, would these internal clocks remain aligned? Or would they drift apart like musicians falling out of sync with the conductor? Because we do not yet know the answers, engineers designing a humane time machine would need to think in terms of temporal cushioning. Just as a car protects its passengers from bumps in the road with soft suspension, a time machine might need to protect its passengers from sudden temporal changes with smooth transitions. Instead of snapping from one timeline to another, the machine could gradually shift the traveller into the new rhythm of spacetime. Think of it as dipping into water slowly rather than diving in head first. This idea extends to what might be called temporal seatbelts, not straps or buckles, but carefully calculated trajectories that ensure the traveller never experiences sudden, sharp changes in curvature. If the machine must navigate near dangerous regions, whether a warp bubble boundary or the mouth of a wormhole, it would do so along paths where space-time varies gently, keeping the passenger wrapped in a cocoon of stability. Of course, even with all these precautions, radiation shielding, gradual acceleration, and carefully smoothed time transitions, there is an unavoidable truth. The human body evolved to live at the surface of a planet under 1 g of gravity and 1 rhythm of time. Anything beyond that is an adventure into the unfamiliar, and that unfamiliarity grows even more profound when we shift our attention from flesh to thought, from the body to the mind. Because while the muscles, bones and cells face their own challenges when travelling through altered time, the mind carries its own delicate dependence on rhythm, memory, continuity and meaning. And if physics stretches those foundations, what happens to the traveller's sense of self? What happens to their connection to the world they left or the world they return to? That question, soft, human, and quietly unsettling, is where our journey drifts next. If the body reacts to time travel with forces and strains, the mind reacts with something more subtle, shifts in orientation, memory, expectation, and meaning. Our thoughts are anchored not only to who we are, but to when we are. We move through life with a quiet certainty that tomorrow follows today, that the past stays where it is, and that our memories line up in a single, unbroken sequence. Time travel, even in its gentlest form, unsettles that foundation, And because the mind is built from rhythms and stories, not merely neurons and chemistry, its challenges are often more delicate than any physical stress. To begin, imagine something simple. You leave on a journey that lasts a single hour for you, but when you return, 10 years have passed for everyone else. This isn't science fiction, it is a natural consequence of time dilation, the soft stretching of time that occurs at high speeds or in strong gravity. Even at speeds far below the speed of light, this stretching is tiny, almost invisible. But push the effect far enough, and the mind faces a jarring disconnect. You left while your friends and family were younger, and you returned to find them older, changed, reshaped by years you never lived. This emotional gap can feel like jet lag of the soul, not because you're tired, but because the thread that connects you to others has shifted. The continuity you depend on, the sense that your life unfolds in parallel with the lives around you, weakens when time passes differently for you than for those you love. The traveller might not have aged, but the world has. And emotionally, that difference creates a quiet, aching distance. Now imagine the reverse, travelling into the past. Even if paradoxes are avoided, whether by self-consistency or branching realities, the psychological toll can be deep. To see a younger version of a loved one no longer alive in your original timeline, or to witness events you've only read about, is to step into a story you were not meant to inhabit. The mind carries memories like threads woven into a tapestry. Stepping into the past tugs at those threads, loosening familiar patterns and revealing uncomfortable new ones. There is also the question of expectation. We walk through life believing that the future is unknown, open. But if time travel ever lets someone glimpse what is ahead, whether decades or centuries, the mind would need to reconcile what it knows with what it feels. Even hearing about the future from other travellers could shift a person's sense of possibility. The mind relies on uncertainty as a kind of psychological buoyancy. Remove too much uncertainty, and the inner landscape becomes strangely still, as if stripped of its winds. A more unsettling possibility is the effect of witnessing things too vast or too ancient for a human perspective. Imagine watching the first human settlements take shape thousands of years ago, knowing how the story ends, or visiting the far future and seeing technologies or cultures so alien they barely resemble what you left behind. These are not just historical observations, they're emotional earthquakes. They shake assumptions you didn't know you had. They challenge your sense of belonging, identity, and place in the grand arc of history. This sense of dislocation might occur even without dramatic time jumps. Simply travelling through a wormhole with a slight time offset, arriving hours or days earlier than someone who took a different route, might produce subtle psychological effects. Memory relies on the idea that causes precede consequences. If you arrive before a letter you mailed or before a message you sent, the mind must contend with sequences that feel inverted. Even if nothing paradoxical happens, these experiences create tiny gaps in the familiar chain of events. Then there is the multiplicity problem, a gentle name for something potentially overwhelming. If branching realities exist, every time traveller could find themselves in a timeline that resembles the one they left, but differs in small, unsettling ways. A painting hung in a different room, a childhood memory slightly altered, a familiar scent missing from a familiar place. These tiny deviations can accumulate, creating what psychologists might one day call temporal dissonance, a steadily growing feeling that the world is almost right, but not quite. Because the mind depends on consistency, even subtle inconsistencies can feel like static in the background of consciousness. Too much of this static might lead to anxiety or a sense of ungroundedness. Travellers could feel disoriented not only in time but in self, unsure whether their own memories belong to the timeline they occupy or to one now inaccessible. To navigate these challenges, the idea of temporal counselling becomes essential. Not counselling in the traditional sense, but a form of preparation and decompression specifically designed for temporal experiences. Before travelling, a person might undergo training to anchor themselves through mental exercises, ways of stabilising identity even when the world changes rapidly. After travelling, especially when returning to a timeline that has aged without them, psychological decompression might help the traveller integrate what they experienced with the life they re-enter. This kind of support becomes even more essential if time travel involves intense relativistic effects, where minutes for the traveller equal decades outside. In such cases, a person might return to find their future waiting for them, not as a distant horizon, but as an immediate fact. Homes changed, cities grown, loved ones older or gone, careers reshaped, dreams fulfilled without them or abandoned long ago. The emotional weight of this can be a sense, even in more controlled forms of time travel, like entering a lab-made loop where only seconds pass outside. There may be effects we cannot predict. The brain is full of delicate rhythms, electrical oscillations, neurotransmitter cycles, sleep patterns, memory consolidation. These rhythms evolved under the assumption that time flows steadily. Altering the flow even slightly might disrupt these cycles in ways we do not yet understand. A traveller might experience changes in mood, focus, or memory integration. They might struggle to reconcile internal and external clocks. This is why a humane time machine design must address not only physics, but psychology. It must ensure the interior environment protects the traveller not only from tidal forces and radiation, but from temporal shock. Smooth transitions, clear orientation cues, and safe arrival protocols become as important as curvature and energy. At its heart, the mind's relationship with time is a relationship with meaning. Our memories create a story, our expectations create a future. When time itself becomes flexible, that story can bend, twist, or fragment. To travel safely through time, we would need not only physical shielding and careful trajectories, but emotional grounding and mental resilience. And once the mind's challenges are understood, another layer emerges, one that extends beyond the traveller to the world they enter. Time travel raises moral questions. How should a machine decide what trips are allowed? What changes are permissible? What responsibilities do travellers have toward the timelines they visit? These questions guide us gently into the next phase of the journey, where the machine's ethics become as important as its physics. Even if we imagine a time machine built with perfect engineering, its space-time architecture smooth and stable, its energy supply drawn from stars, its negative energy scaffolding held in delicate balance, there remains a quieter, deeper challenge. A time machine is not simply a vessel, it is a doorway into stories that have already unfolded or have yet to begin. And doors, by their nature, invite questions of choice, responsibility, and restraint. If we ever built such a machine, we would need something like a moral compass woven into its design, something that ensures not only physical safety, but the safety of entire histories. This idea may sound abstract, but it begins with a simple observation. Time travel, even in the gentlest form, can influence events. It might be as small as a conversation that shouldn't have happened, or as large as altering the outcome of a major turning point. And while fiction enjoys the drama of such changes, reality would demand caution so careful that it becomes part of the machine itself. Imagine stepping into a time machine without guidance. You dial in a date, the machine opens a corridor, and suddenly you stand in a moment that was never meant to include you. Even your quiet presence could shift probabilities. A missed appointment, a delayed carriage, a sentence overheard. The smallest nudge might ripple outward like circles in water. Because of this, a responsible time machine cannot rely solely on the judgment of travellers. It must participate, offering not only transportation but ethical navigation. To envision such a system, we can begin with the idea of a guardian algorithm, a soft, thoughtful intelligence embedded within the machine. Not a cold enforcer of rules, but a gentle advisor, evaluating each proposed journey with the same care a navigator uses when reading dangerous currents. Before opening a path, the machine might ask, "What are the potential consequences of this visit? Does this moment sit at a sensitive branch in history? Will the traveller's presence introduce risks that cannot be reversed?" For example, the machine might prevent travel to pivotal moments that shape the future so deeply that even the smallest disturbance could cascade into immense change. It might refuse access to years where entire civilizations hinge on fragile decisions. It might steer travellers away from events whose outcomes define the lives of millions. And while this may sound restrictive, it is the same kind of caution we now build into self-driving cars, medical AI systems, or industrial robots. Safety is not a barrier to exploration. It is the foundation that makes exploration survivable. The idea of temporal locks arises here, mechanisms that prevent repeated visits to the same moment, or that limit how close one can come to specific historical events. These are not locks in the literal sense, but protections within the geometry of the machine. If a traveller tries to reach a moment already visited, the machine might find the curvature too unstable to maintain. If someone attempts to approach a critical event, the machine might redirect them to a safe window a little further away. It's similar to the way a pilot avoids flying directly through a storm. The machine senses turbulence, not atmospheric turbulence, but temporal turbulence, and adjusts its trajectory accordingly. To make this more intuitive, imagine you're looking at a tapestry woven with many threads. Some threads are decorative, some structural, and some so essential that removing them causes the entire pattern to unravel. Time travel interacts with these threads. The machine must know which ones cannot be touched. And because travellers cannot perceive the hidden structure of time directly, the machine must be their guide. Another aspect of this moral compass is prevention of weaponization. A time machine, if misused, could become not a tool of exploration, but a devastating instrument. Imagine someone with harmful intent travelling to a moment of vulnerability in history, or using future knowledge to manipulate the present. Even without paradoxes, such actions could reshape societies in ways that undermine freedom, stability, or dignity. To guard against this, the machine would need internal protocols, quiet, unwavering rules that prevent trips which carry clear signs of destructive intent. These rules could be based on patterns, sudden requests for specific dates tied to disasters, attempts to enter regions under high instability, or traveller profiles indicating harmful motivations. The machine might simply refuse to open its gateway until it senses a safe and ethical alignment between the traveller's purpose and the proposed moment. This isn't moral policing in a human sense. It's an extension of the machine's responsibility not to destabilize the very world it exists within. But designing such a moral compass raises a paradox of its own. Ethics evolve. What one century believes is noble, another may question. Values shift with culture, with knowledge, with time itself. If the machine's rules are fixed, they may become outdated. If the rules adapt, who decides how they adapt? A system designed to prevent harm today might interpret different events in tomorrow's context, and if the machine can travel across centuries, its ethical framework must be robust enough to remain compassionate across enormous spans of human experience. One possible solution is for the machine to be guided not by rigid laws, but by principles, soft, universal considerations that transcend specific cultures. These principles might include protection of life, respect for autonomy, avoidance of large-scale harm, and preservation of historical integrity. Instead of telling the machine exactly what to forbid, we teach it how to weigh possibilities the way a thoughtful person might, but with the precision and patience of something that never grows tired or overwhelmed. To maintain this adaptability, the machine may need to observe history as it unfolds, learning from patterns the way advanced AI systems learn from vast datasets today. But unlike traditional AI, which is often focused on prediction or optimization, this system would focus on subtlety, understanding when a traveller's presence is safe, when it is neutral, and when it risks pulling threads too tightly. Throughout all of this, the machine must remain transparent to its passenger. Instead of issuing cold denials, it might explain its reasoning gently, why a certain moment is too fragile, why a certain path is unsafe. Travellers would not be fighting a machine's authority, but collaborating with its wisdom, learning to see time not just as a sequence of moments, but as a living web. And in this partnership between human and machine, we find an echo of the larger theme, that time travel is not just a technical challenge, it is a moral one. It asks us to consider not only what we can do, but what we should do. And as we drift toward the final stages of our exploration, we discover that the machine's moral compass reflects our own. It mirrors our hopes, our fears, and our desire to move through time responsibly. Even when that movement defies everything we thought we knew, the next step brings us toward a different kind of possibility. Not the ability to rewrite the past, but the gentle recognition that the future might already be shaping itself around us, and that the most realistic time machines may guide us forward, not backward, through the river of time. Most visions of time travel involve stepping backward, toward ancient cities, forgotten landscapes, or pivotal moments etched in the world's memory. But when we listen closely to the physics we understand today, and the limits hinted at by paradoxes and quantum negotiations, a quiet truth emerges. Travelling into the future is not only easier than travelling into the past, it is already a natural part of how the universe works. And if time machines ever exist, they may be machines that shape how we move forward, not machines that rewrite what has already been lived. A gentle way to approach this idea is through relativity, the soft rule book that governs how time flows. Time is not absolute. It stretches depending on motion and gravity. When you move quickly, very quickly, time slows down for you compared to someone standing still. When you orbit close to a massive object, your seconds lengthen, unfolding slightly more slowly than the seconds in calm, distant space. This isn't a theory in the abstract. We observe it every day with satellites orbiting Earth. Their clocks drift gently compared to our clocks. They tick faster because they are farther from Earth's gravity. We correct for this constantly, so navigation and timing systems remain accurate. Now imagine taking this gentle stretching and amplifying it. If you travel at speeds close to the speed of light, for every hour you experience, months or years might pass for the rest of the universe. Move close to a black hole. Without crossing its dangerous threshold, and minutes for you may equal decades elsewhere. In these scenarios, you're not breaking time, you're sliding along one of its natural curves. The result is a one-way ticket into the future. This kind of journey has no paradox. You don't return to your own past. You simply find yourself in a later chapter of the world's story, as if the universe turned its pages faster for everyone but you. A time machine built around this principle would not resist the laws of physics, it would embrace them. Such a device might look like a spacecraft wrapped in shielding and advanced geometry, designed to endure the intense acceleration needed to approach light speed. Or it could station itself near the edge of an engineered gravitational field, perhaps a ring of dense plasma or a controlled singularity, allowing the traveller's time to slow dramatically while the world outside races ahead. This is time travel as nature allows it, gentle, lawful, stable. And yet, even this form of travel carries emotional weight. Imagine leaving for a brief mission and returning to find the world age without you. Great-grandchildren you never met, technologies you never studied, a skyline transformed, a language subtly changed. You are still yourself, but the world has slipped forward. In a sense, the future knew you were coming, but it continued without waiting for you. A machine that uses this kind of time dilation must therefore prepare the traveller not only physically, but emotionally. Training must help the traveller understand the passage of outside time, anchor their identity, and prepare for a world that evolved independently of their choices. But there is a deeper possibility, one that lies between the gentle curves of relativity and the delicate shapes of engineered space-time, messages sent to the future. Imagine a time machine not as a cabin someone steps into, but as a device that allows information to travel forward through controlled time dilation. A probe might orbit near an intense gravitational field, experiencing minutes while centuries pass outside. It collects knowledge, makes observations, waits for the right moment, then returns to deliver what it has learned to the future. This isn't rewriting history, it's delivering insight directly into the hands of future generations. Such devices might help scientists test predictions about climate, physics, or cosmic evolution. They might allow medical research to unfold in accelerated form, linking decades of progress to minutes of subjective time. They might let us explore deep space without waiting lifetimes for signals to return. In this sense, time machines become tools for forward communication, not backward intervention. And there is a gentler variant, temporal bubbles, laboratories where time flows differently inside than outside. Researchers could conduct decades of experiments, while only hours pass in the world beyond. This kind of time manipulation avoids paradox entirely, because the bubble is isolated. Nothing inside can influence earlier moments outside. It is like building a lighthouse whose beam points only one way, forward. Some theories even allow for tiny closed loops that exist only within the bubble. These loops might accelerate computations, stabilize quantum processes, or test exotic physics without affecting the outside world. Such design stays safely within the universe's causality rules, respecting the chronological flow while still exploring the frontier of time. These limited forms of time travel, forward travel, isolated loops, time-dilated laboratories, are gentle on reality. They require no paradox protections. They ask for precision and energy, but they do not threaten the structure of cause and effect. And so, in a very real sense, they may be the most realistic time machines humanity will ever build. They also blur the boundary between engineering and philosophy. What is the meaning of future if someone can reach it in days? What is the meaning of patience, of progress, of legacy? If you can step into a machine and let a century pass in silence, what does that say about our relationship with time's natural flow? There's another gentle twist to consider. If such machines exist, the future must account for their presence. Every timeline that includes time travelers must accommodate their arrival, not as paradox makers, but as participants. The world grows around the knowledge that people may step out of stasis or out of high-speed journeys, carrying the past with them like a memory sealed in glass. Communities might form around these travellers, people who lived through one era of history while the world leapt forward. They might become storytellers, bridges between ages, reminders that while time moves steadily, human experiences do not always flow at the same rate. In these possibilities, we see time travel not as a tool for changing history, but as a tool for expanding human experience. A way to see far futures without breaking the past. A way to let knowledge leap across centuries. A way to soften the harsh edges of time's arrow without bending it backward. And in that quiet realization, another truth emerges. Even the most powerful time machines, grounded in physics and guided by ethics, lead us toward a deeper question. Not whether we can travel across the river of time, but what that river truly means for our lives, our choices, and our sense of presence. That question waits in the final session of our journey, where we gently gather everything we've explored: physics, paradoxes, human resilience, and moral responsibility, and let it settle into a soft verdict about the nature of time itself. Now that we've wandered through the entire landscape, through wormholes and warp bubbles, stellar engines and negative energy, paradoxes and quantum loops, human bodies and human hearts, we can pause in a quiet clearing. The machinery fades into the background, the equations soften into metaphors, and what remains is a simple, almost tender question. After all this exploration, what have time machines really taught us about time? The first lesson is that time is not the rigid ticking line we grow up imagining. It is flexible, responsive, almost alive in its own way. It stretches near heavy objects, relaxes in open space, slows for travellers moving quickly, and dances with probabilities at the quantum level. If space is a landscape, time is the breeze moving across it, never perfectly uniform, always shaped by its surroundings. Time machines, at their core, are not attempts to break this rhythm, but attempts to listen closely enough to shape it. The second lesson is that bending time is not easy, not because nature is cruel, but because nature is delicate. The architecture required, those tunnels, loops, bubbles, demands precision beyond anything our hands or tools can yet manage. To sculpt space-time, we would need energies on the scale of stars, materials that nudge, the vacuum itself, and control systems capable of reading and adjusting the geometry with the subtlety of a musician tuning a violin mid-performance. The more we understand the complexity, the more we see that time is not a doorway waiting to be opened. It is a tapestry woven with threads we're only beginning to see. The third lesson is that the universe prefers stories without contradictions. Not in a moral sense, but in a logical one. Cause must precede effect, not because of cosmic law enforcement, but because reality itself becomes unstable when that order frays. Hawking's vision of a chronology protection mechanism isn't a punishment. It is a quiet safety feature. If a machine tries to fold time into a loop that breaks coherence, the vacuum churns in resistance, filling the region with energy until the structure can no longer hold. It is the universe's way of saying, the past is not a playground. The story has already been written. The fourth lesson is about us, our bodies, our minds, our place in time. We are creatures tuned to one rhythm. Our hearts beat in seconds that never vary. Our memories arrange themselves in neat linear threads. Our emotions grow from continuity. Yesterday follows from the day before, and tomorrow rises from today. When time stretches differently for the traveller than for the world they leave, the result is not only physical stress, but emotional disorientation. A traveller who returns to find decades passed in an hour carries a burden not of physics, but of meaning. They become a person out of sync, a visitor in their own future. A machine that moves through time then must also be a caretaker of bodies, of minds, of identities. It must shield the traveller not only from radiation and tidal forces, but from dislocation, shock, and solitude. It must offer gentle transitions, clear grounding, and the psychological equivalent of a soft landing. The fifth lesson is ethical. Time machines, even the gentlest ones, must carry a moral compass. They cannot be built as instruments of manipulation. They cannot be allowed to alter pivotal events or reshape histories that do not belong to the traveller. If the machine opens paths through time, it must also guard them, refusing dangerous journeys, redirecting unstable ones, and guiding travellers away from moments where harm outweighs curiosity. Perhaps the most surprising lesson, though, is this. When we strip away the drama, time machines begin to look less like devices for escaping the present and more like tools for deepening our understanding of it. A warp bubble drifting forward in time is still bound to the river of causality. A wormhole that cannot form a paradox still honours the narrative of the universe. A traveller who moves faster into the future still returns to a world shaped by choices they never witnessed. Even the most advanced form of forward time travel, slowing your own clock through high-speed journeys or strong gravity, does not let you rewrite anything. It simply carries you forward at a different pace, like a boat drifting in a faster current. The future you arrive in already contains your arrival. The river knew you were coming. And so, we reach a quiet truth. The universe seems exquisitely designed to protect its own story, not aggressively, not stubbornly, but gently, through physics, through logic, through the natural sensitivity of quantum fields. The past remains stable, not because it is guarded by cosmic law, but because it is an integral part of the structure that holds everything together. This could be disappointing. It could feel like a door closing. But there is another way to see it, softer, more intimate. If the past cannot be undone, then each moment becomes precious. Every choice matters because it cannot be rewritten. Every memory is irreplaceable because it cannot be revisited except through the quiet time machine we carry inside us. The mind's ability to recall, to dream, to imagine. In this sense, we already possess the gentlest form of time travel, and if the future is the direction the universe permits us to explore, then the future becomes not a threat but an invitation. It becomes a place we travel to not through machines, but through choices, decisions, and hopes. Technology may one day let us move through that future at different paces, but it will still be the future we shape together. In the end, the idea of a time machine teaches us more about ourselves than about exotic physics. It shows us how deeply we long to understand our own story, to revisit what was lost, to glimpse what might be. It reminds us that time is both vast and intimate, cosmic in scale, personal in feeling, and it reveals that even if we never build a device that can carry us backward, we live within a universe that carries us forward with remarkable grace. As this quiet exploration comes to a close, imagine yourself once more floating in that gentle darkness between stars. The hum of possibility softens, the air becomes still, time resumes its familiar pace, flowing around you like a calm river. And whether your eyes are open or drifting closed, whether you're listening from the far future or the quiet moments of tonight, thank you for walking through these ideas, slowly, softly, curiously. If you'd like to return to this calm corner of the cosmos again, you are always welcome. For now, rest. Let time take the lead. Let the moment settle like a warm blanket, and let yourself drift peacefully into whatever comes next.